Okay, so first thing, there was the practice 3 built in was just generating another polynomial. You'd follow the exact same procedure we did back here. So like you'd say, okay, this time, or I got my derivatives, I know what they are, they equal the constants. So this is how it comes out. Again, you could either leave it simplified or unsimplified, it doesn't matter to me. And then the guy threw in a bonus question. He said, is there an extreme value there? If so, what is it? It's kind of a good throwback, right? So you know it's at least a candidate because the first derivative is 0. And then you say, well, but I know it's concave down there. So if its first derivative is 0, so if its slope is 0, but it's concave down, it's got to be a max. And then the other one was an old school algebra 2 problem. You got a vertex, you got a point, build the quadratic. Okay, so how about the good stuff then? What do you think? What's the good stuff here? Nothing? Not really. I thought if nothing else, like on the first page, again, the explanation of where the factorials come from. They either come from successful derivative, or not successful, sequential derivatives, or in the way we did it first would be sequential antiderivatives. Kind of a good reminder of where that comes from. Otherwise, the rest of the first 2 pages was pretty much exactly what we did together. I thought maybe that stuff would kind of be better to do together than get out of the book. If you have any good stuff from page 35, I'll happily take your suggestion for highlighting, but I honestly didn't actually come up with anything because, again, it was mostly just work. 36 and 37, though, I thought were full of good stuff. So here was the actual explanation of the factorials. And again, this is just something that I do. You don't have to do it. To avoid covering the entire page in yellow ink, sometimes when I'm highlighting stuff, I'll try and make a coherent sentence out of little bits and pieces. So for example, factorials are the product of subsequent differentiation. Or you could keep going and say, as the powers become coefficients. You could certainly decide to include that if you wanted. But see how we just get a few things there and it stands out. We're going back night before, quiz, test, whatever. Oh, factorials are the product of successful differentiation. I don't actually have to read 4 sentences to come up with that, or whatever it would have been. Blah, 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 blah. Observation, we need this many pieces of information. And then we expand on what pieces of information actually means later on. The author does. For us, for Taylor polynomials, that's going to be values of the function and its derivative somewhere. And wherever that particular x value is, that's the center. And then, so turning the page here. Too far. There we go. There I am. This is the key idea of all this Taylor polynomial stuff. If you know a bunch of derivatives at a single point, if you know a bunch of rates of change of a function at a single point, you can use that to actually build an entire polynomial function. I just think that's crazy. You might say, okay, like, what's the point of that? Who cares? This is really helpful, not only for coming up with functions that approximate those hard to evaluate ones like sine, cosine, e to the x, whatever. This is also useful when you're in uncharted territory. For example, if you don't actually have a function that represents something, you can still build one if you can measure an amount, a rate of change, and how that rate of change is changing a few times. So like, when I first started teaching this, I was like, I don't understand why we have to teach. What's the point of this? And my wife was like, you're an idiot. This is how we do chemistry. Well, you don't just have a magic function that explains how quickly this reaction occurs, but if you know how much reactant you have right now, and you know how quickly it's reacting, and maybe you can measure how quickly that reactingness is changing, then you can build a polynomial that actually has that relationship. Isn't that cool? That's so cool!
I mean, some of them are just going to be bounded from like x equals 0
Yeah.
to x equals 1.
Yeah.
And how will we determine where they're bounded to?
But Charles, chemistry.
So, Charles reminds us of essential question number
Oh, get him.
2 and 3,
Oh.
really. 2 and 3, which we will investigate a little bit in section 4. So the next one. Right here, we're just focused on building said polynomial. In the next section, we'll look at how much can it be wrong by. That'll be like quantifying error at a specific place. And then, you're going to hate this answer. In sections 6, 7, and 8, we're going to work on specifically nailing down that domain exactly, where we can get a perfect fit, and then outside that, it's no good. So it takes a while. But I do promise we're going to address your question in the long term. He really does not look satisfied with that answer.
Charles is ready. He's ready to move on to section 2. It doesn't
It doesn't really find something for. It doesn't really. I guess since we're not at section 6, 7, 8, 9 yet, it doesn't really make sense to me how we could get a function for some phenomena in nature, and then find the domain for where it actually fits.
Yes. Okay, I got you. Yes.
Yes. C.
Okay, so I guess your question. Okay, we're gonna have to cut your question into 2 parts. You're right. If you don't have anything to compare to, you don't know how much error you have. All you know is that the farther away you get from the center, the worse your thing's going to be. But the more terms you have, more derivatives you measure, the more accurate it's going to be. Okay, so that's fair. If we're comparing to something that we can force a graphing calculator to graph for us, then we can nail down that domain exactly. So we'll address one of those more than the other, but I understand your concern. Anyway, back here. Where were we? So this guy here is kind of a rule. Well, I mean, it definitely is a rule. It's in word form. Down here, it's the exact same rule, but in like math speak. So whatever makes more sense to you, or both. Neither. Basically, when you're building these magic polynomials, not only do they have to be perfect wherever you decide to build them, so right at the exact point, the exact center, the polynomial has to be a perfect match of the function, but the first n derivatives do as well. So if you're using like 5 derivatives to make your polynomial, you're probably going to end up with something quintic. Okay, all 5 of those derivatives have to match the 5 derivatives of the original function. You just going to leave it there?
Give me 2 seconds.
Okay.
1, 2.
In other words, the polynomial's y value has to match the function's y value. The polynomial's first derivative has to match the function's first derivative, and so on, all the way down until you get to however many terms, degrees, nope, not terms, however many degrees you've used. So again, hopefully that's reasonable, because not only should we have a perfect point, we should have something that has a decent slope relative to the thing we're trying to model. Then we should try and have something that has a similar concavity. The concavity should change at a similar rate, something like that. And then, hey, remember the other day when we were collecting the observation, when we were collecting the observations, the author collected observations about these polynomials, and number one was, hey, they're perfect at the center. There it is. Now it's a rule. That was an observation before. I told you, hey, this is going to be a rule. There it is. Okay. Let's see. Let me think. We got 15 minutes left, and you guys have done great work. I don't want to drive your nose into the ground with this. So how about to be ready for Monday, I'm going to task you with finishing this. There's 1, 2, I think 4 more. Yeah, 4 more pages. One of them, a page and a half, is just straight example. So it's actually not a whole lot of reading. Let me just point out a few things for you. Oh, I guess we didn't summarize in your notebook either. We can do that too. Let me point out a few things for you. So we'll come back to these. We can talk about these right now. And then in the reading, you're just going to hit on these two over the weekend. Oh, no, we haven't gotten to this one yet either. Okay. So at this point, we kind of can only talk about this one here. So for the weekend, you're going to be looking for these 3. I want to actually just go into that real quick. All right. In your book, flip to page 39 real quick. You'll see this scary looking box at the bottom. Looks pretty scary, right? That is your definition here. That's your second bullet point. So what we're going to be trying to do, either over the weekend or first thing Monday morning, is we're going to be trying to turn that into words. Okay? And we can do that together if you can't figure it out. Then, furthermore, flip to page 41. At the bottom of your notebook, I say, box the top 4 equations on page 41. We need to memorize these 2. Sad face. That would be these top 4 guys right here. College Board assumes you have memorized all 4 of these when you walk into the AP exam. I'll give you a couple things. First, real quick, they are all centered at 0. So officially these are all Maclaurin polynomials, but they're also Taylor's. But I do want to give you some advice since we have to memorize them. So I'm going to say memorize. Memorize. But I want to make your life a little easier. When you memorize these, use U instead of X. And I think that will make it easier for you to see how to make those substitutions and whatnot that you had to make in the homework to be ready for today. So for example, like the first one would really be e to the u, and this one gets proved literally in the first example that you're going to read. So ignore the fact that you haven't seen this one yet. E to the u is really 1 plus u squared over 2 factorial down the line. Same thing for the rest. I think that makes it easier to substitute in. As for the rest, they are not required memorization. The bad news is you can build any of these from this 4th one. So this 4th one should look familiar. It was one of the ones we worked with a lot in the last section. And remember how you, like, in the homework you had to make a substitution to make it 1 plus x instead of 1 minus x. Or you had to make it 1 plus x squared. That was another homework problem. And you had to integrate it. You can integrate it to get to this natural log, or you can integrate and make a substitution to get this natural log x plus 1. Or you can integrate the 1 over x plus 1 plus x squared to get to arctan. Your life can get a little easier if you memorize these 2. But you don't have to. you can always generate these as long as you know the first 4. Actually the bottom 5. Basically, they would just save you time. When I say make your life easier, I actually just mean save you time. Can we do a gateway?
Actually, you're right.
This is a trick. You know, I will consider it.
Yeah.
No, please.
We should put 10 extra points.
I will
Gateway.
consider this.
Points,
Okay.
I'll consider this. So again, we have to know the top 4. If you know the top 4, you can generate any of these bottom 5. I know some of you guys are here because you're really good at memorizing stuff. If you got a photographic memory or you're really good at memorizing stuff, might be worth the 5-10 minutes it would take you to get the rest of these, because that could save you time further down the road. If you're not great at that, just remember you can make them from the top 4. Okay. I'm gonna let you go. Your homework then for the weekend is just finish the reading, highlight, work on some of your notes and summary. That'll be the first thing we do. Finish highlighting, make sure we all got the same ideas out, and then we'll do some practice problems. We'll get started on the assignment.